what I have planned for today, now that we've got the roll taken care of, is we are going to simulate the circuit that we worked on Wednesday to make sure that our analysis was correct. So effectively, we have to actually do a reasonable amount of work to figure out whether or not we got that second order differential equation right. So we're going to do that, and then we're going to work a problem with two of the same energy storage elements in it. And then we'll use the rest of the class for some sort of exam review if any of you guys want it. So this resistor R1, if I'm not mistaken, was a 4 ohm resistor. Let me look at my, yes, a 4 ohm, 0.5 milli, 10 ohm, 2 Henry. As per usual, I'm going to place ground at the negative polarity terminal of my capacitor, and I'm going to label the positive polarity terminal of my capacitor VC. I need to put my initial conditions in. So the voltage at node VC is going to be equal to, let's see what we found at T is equal to 0 minus. So at T is equal to 0 minus, the voltage drop across the capacitor was 5 volts. And while we're here, the current flowing through the inductor was 0.5 amp. So that is equal to 5 dot IC I L1 5, like so. And what did we calculate? S1 was -7. Let's see. So let's do, I think 1 second should be okay, but we'll find out. And if I'm not mistaken, we solved for the capacitor current. Okay, so 1 second is obviously far too long. So let's look at let's look at 20 milliseconds. Milliseconds seems reasonable. Okay. So now what I'm going to do, scroll all the way down to the bottom. Oh, there was our solution. And I'm just going to type those numbers in. Okay. So 7.231 times 10 to the -3, because that's in milliamps, times exp of, let's see, what was S1, -7.0. Multiply that by time. And then -1.757. -497 point something. 971. And it matches. So if all of our analysis matches, then obviously we got our second order differential equation correct. If the simulation does not match, or our analytical solution does not match the simulation, then it's a little bit more tedious of figuring out, okay, did I make a mistake in the analysis at t is equal to 0 minus or t is equal to 0 plus? Did I make a mistake in calculating alpha and omega naught, or did I make a mistake in the sometimes terrifying amount of algebra that is required to develop that second order differential equation? So I would encourage everybody to be ludicrously meticulous about the algebra that they're doing when deriving that differential equation, because that's where probably the most common mistakes are going to be. All right, so anybody have any questions, comments, or concerns regarding this simulation? I hope at this point it's pretty much old hat. So what we're going to do now is work a new problem. My laptop plugged up. It contains two same type energy storage elements. So our circuit in question here will be this guy. Let's have a 20-volt source connected to a 4-ohm resistor, which is connected to a switch that is going to close at t is equal to 0. We will have a 2 Henry inductor here. Then let's have a 6-ohm resistor over here and an additional 2 Henry inductor over here. Okay. So the first thing that we would do is determine whether this is a series RLC circuit, a parallel RLC circuit, or a general RLC circuit. Which type is this? Or I guess not a general RLC circuit, a general second order circuit in this case. So it's obviously not series or parallel RLC because there's no capacitor in here. So then the question becomes, could we simplify this to a simple RL circuit or not? And the answer here is no, right? So during the transient condition, dead network, we are going to see the 2 Henry inductor effectively in parallel with the 4-ohm resistor. I'm saying that because we turn the voltage source off to see what it looks like, right? So we have 2 Henrys in parallel with 4 ohms, and that is in parallel with a combination of 6 ohms in series with 2 Henrys. There's no way that we can combine those two resistors, and there's no way that we can combine those two inductors. So these are two discrete energy storage elements, which means this is going to behave similarly to a general RLC circuit. So we're going to call this type of circuit a general second order circuit. Okay. So our goal here, I'm going to label this inductor current as IX. I'm going to call this one IY. And our goal is to get a second order differential equation in terms of only IX or only IY. All right. And while we're at it, I'm going to call this voltage Vx of t, and I'm going to call this voltage Vy of t. And let's say that our ultimate goal is to figure out Vy of t in this particular example. All right, so how do we figure out what our second order differential equation is going to be? I'm taking you guys' suggestions today.
Can't determine alpha or omega naught values.
We cannot determine alpha or omega naught until we get our second order differential equation. That's correct.
Should we start analyzing at t equals -0?
So we can't do that. We're trying to figure out, so our first step is always to calculate alpha and omega naught. And in order to do that, we have to develop our second order differential equation. So that I repeat my question, how are we going to get our second order differential equation? It's always developed during the transient condition, which means for t greater than 0 plus, okay? And as I mentioned in class on Wednesday, we can use things like nodal analysis and mesh analysis, but to me, that gets pretty difficult pretty quickly. Typically speaking, relying on things like Kirchhoff's current law and Kirchhoff's voltage law seem quite a bit easier to me, okay? So let's do this extraordinarily similarly to what we did with the problem on Wednesday, okay? Let's apply KCL at this node X. And see what falls out, okay? So during the transient condition, the switch is closed. So we have a current of something flowing in, and then we have two inductor currents flowing out, right? So we could say that Ix, which is an inductor current of T, plus Iy, which is an inductor current, is going to be equal to the current flowing in. How do I represent the current flowing through the 4 ohm resistor into node X? How do I represent that? So the voltage drop across the resistor divided by the resistor value gives us the current. Yep, good old Ohm's law is absolutely applicable. So what's the voltage drop across the resistor? A whole transient. All we're doing for the next probably 10 minutes is during the transient condition. What was the suggestion? I disagree. I disagree. It's not going to be a DC value.
Do we need a Thevenin?
Nope.
Resistance?
You're putting too much. You're trying too hard.
The circuit is dead, isn't it? Or
No. So during the transient condition, okay? So that just means this switch is closed and we're analyzing this circuit as a function of time. So the voltage at this side of the resistor is 20 volts. The voltage at this side of the resistor is Vx. So 20 minus Vx over 4 ohms. It doesn't have to be hard. Okay. We are treating effectively this node as a reference node. We don't have to because we get the exact same result if we just did KVL around that loop to find the current flowing through that portion. So 20 volts minus Vx of t over 4 ohms. All right. Now, we're going to play around with this a little bit. Okay. One big reason that we're going to play around with it is because we know that Vx of t is related to Ix of t, because Vx is just the voltage drop over an inductor and Ix is the current flowing through an inductor, right? So we could say Ix of t plus Iy of t is equal to 20 volts over 4 ohms, which is 5 amps, right? Minus Vx. Oh, actually, hold on. Before we even do this, I want to do one thing here. And my apologies. I'm going to call this resistor R1, this guy R2, this guy L1, and this guy L2, so that I can do it symbolically so that I don't wind up making a simple algebraic mistake later on. So just to be clear, I'm going to then erase this 4 ohm bit here and call it R1. And so let's call this VS. My apologies for telling you to do exactly this on Wednesday and then not doing it. Seems like something I do. So VS over R1 minus 1 over R1. So how do we express Vx in terms of Ix? L di dt, right? So that's going to put L1 in the numerator and then dIx of t by dt, like so. Connor?
I apologize, it's a little bit regressive, but the resistance of those inductors and capacitors, there is direct division that you can do.
That is correct.
Okay. I
Right.
don't necessarily need a detail that as long as you can give me that confidence.
Yeah, so it's a derivative-based relationship between voltage and current for resistors and capacitors for these circuits. Once we get into steady state sinusoidal analysis, then we can utilize the concept of impedance to have a simple linear relationship between a linear relationship in the frequency domain that would allow us to effectively have that simple current voltage relationship like we have for resistors.
Thank you.
Okay. All right, so this is better, but it's not, let's call it great, but we can, so what I mean by that is that this equation is good because it's in terms of just our inductor currents for sure. I'd be willing to bet a reasonable sum of money that we are going to have to manipulate this expression further later on. What I mean by that specifically is we could rearrange this guy right now and we could have IY on one side of the equation and IX in constant terms on the other side so that we would know what IY is as a function of IX, which might prove useful. So like I said, I'd be willing to bet money that we're going to have to manipulate this guy, but let's call this equation 1 for now. So I'm going to put 1 and then a question mark by it because I feel strongly that we're going to mess with it further. But this is a solid relationship. All right, what should we do next? KVL around the right-hand loop seems perfectly reasonable. So we can see that our voltage Vx is equal to the voltage drop over the 6 ohm resistor plus the voltage Vy. Okay. So KVL around the right-hand loop gives us Vx is equal to Vx is equal to the voltage drop over the 6 ohm resistor, which is just R2 times IY plus the voltage drop over the 2 Henry inductor, which is Vy. And now we're obviously going to need to express both of these voltage drops, Vx and Vy, in terms of the inductor currents. So that's going to look like L1 dIx by dt is equal to R2 times IY plus L2 DIY by dt. And this is another good equation that we might have to manipulate further, okay? So let's think about what we have here, okay? We have an expression here, our KVL relationship. We have the we have the first derivative of Ix is related to Iy plus the first derivative of Iy with some coefficients thrown in there. And in equation 1 question mark, we have a means by which we can get Iy simply in terms of Ix. So if we rearranged equation 1, we could pretty easily substitute that relationship into here. So I think that's what we're going to do. All right. So we're going to call this equation 2 for sure. And we are going to further manipulate equation 1 to suit our needs. So by that, I mean, I'm going to leave Iy by itself. So I'm going to have Vs over R1 minus Ix minus L1 over R1 dix by dt. Did I do my algebra correctly here? All I'm trying to do is pull this factor of Ix of t to the right-hand side of the equal sign. Okay. I think I did correctly by putting a negative sign in front of it. All right. So let's call that the real equation 1. And now I need the derivative of Iy expressed only in terms of Ix, which I can get by taking the derivative of equation 1 with respect to time. Right. So d Iy by dt. So what's the derivative of that constant term? 0. All right. What's the derivative of negative Ix? The derivative of Ix, right? So negative dix by dt minus L1 over R1, and then the second derivative, like so. Let's call this guy 3. And we're now going to substitute equation 1 and 3 into 2. And then we're in the home stretch. At this point, it's only algebra, no more circuit analysis whatsoever. So L dix by dt is equal to R2 times Iy of t, where that is Vs over R1 minus Ix of t minus L1 over R1 dix of t plus L2 times negative dix of t by dt minus L1 over R1 times the second derivative. Like so. It is not a coincidence that all of our Ix terms on the right-hand side wound up having a negative sign so that we can simply move them over to the right-hand side and make them positive, right? So let's see, I'm going to just rearrange this expression now. So my second derivative term, when I move it to the left-hand side, it looks like I'm going to have positive L1 times L2 over R1. Excuse me, that should be a T. Right, and that's taking care of this guy right here. Now we're going to do our first derivative terms. So we have just an L by itself. So let's double check and figure out what subscript I missed. I believe that is coming from this L1 here. So this guy is supposed to have a subscript of 1. So we have an L1 term from this guy right here. We have an L1 times R2 over R1 term that's coming from this guy. Right? So I have R2 times L1 over R1. When I move it to the left-hand side, I'm flipping the sign. And then finally, I'm going to have plus L2 from this term right here. All of this is being multiplied by the derivative of Ix with respect to time. And then the only terms that I have left, I have a factor of R2 times Ix. And this will equal Vs times R2 over R1. Everything seem okay? So what's our last step to do here, Bradley?
So we have our second order equation.
Right, but
So
we need a second order differential equation where the coefficient of the second derivative term is 1, which means we need to divide everything by that guy right there. So dividing through by that is the same as multiplying through by the reciprocal. So that's going to give me the second derivative plus R1 times L1 plus L1 R2 over R1 plus L2, all divided by L1 times L2 times the first derivative plus R1 R2 over L1 L2 times the 0th derivative is equal to Vs R2 over L1 L2, if I've done my algebra correctly there. I'm attempting to multiply through by R1 over L1 times L2. I feel pretty strongly that I got that part right. Feel pretty strongly that I got that part right. And when I put the R1 in the numerator, that's going to get rid of this R1 in the denominator. And that's why it's going to look like Vs R2 over L1 L2. All right, so at this point, we could calculate alpha, calculate omega naught, and go about our merry way. Do we actually want to go through those steps, or are we good here that we've beaten everything else to death? Pardon? Sure. All right.
Saying
It's not going to hurt my feelings. Yeah. All right. So alpha here is then going to be, so it's this coefficient over 2. So that's R1, L1 plus L1 R2 over R1 plus L2, all divided by twice L1 L2. Let's throw that in a calculator. Remember to bring mine this time, so I won't have to steal Catherine's. So R1 was the 4 ohm resistor, all right? Sorry, that was slightly too far. So we're gonna have 4 times 2 plus 2 times 6 over 4. Plus another 2 divided by 2 times 2 times 2. So I get 3.5 neppers per second. Omega naught is going to be the square root of R1, R2 over L1, L2. That's the square root of 6 times 4 over 2 times 2, or the square root of 6 radians per second, where the square root of 6 is 2.449 and some change radians per second. So is this circuit overdamped or underdamped or critically damped? It's overdamped because alpha is greater than omega naught. Absolutely right. So we have an overdamped circuit. So just for the sake of argument, let's go ahead and calculate S1, which is negative alpha plus the square root of alpha squared minus omega naught squared. So negative 3.5 plus the square root of 3.5 squared minus the square root of 6 squared is just going to look like 6. I get negative 1 per second. S2 is negative alpha minus the square root of alpha squared minus omega naught squared. And I get negative 6 per second. We okay with these numbers? Anybody actually calculate them other than me? All right. So from here, we're at the point where we analyze that t is equal to 0 minus, t is equal to 0 plus, and in this case, we will have to analyze that t is equal to infinity because the voltage source is connected to the energy storage elements during the transient condition. All right, so at t is equal to 0 minus, our circuit looks like this. We have a 20-volt source in series with a 4 ohm resistor. Our inductor L1 looks like a short circuit. Here we have a 6 ohm resistor, and our inductor L2 looks like a short circuit. So let's call this Ix of 0 minus, Iy of 0 minus, Vx of 0 minus, and finally Vy of 0 minus. So you're 100% correct. You are 100% correct there. I have made a mistake. You're absolutely right. The switch is on the right-hand side of the 4 ohm resistor. Yeah, you're 100% correct. I have made a mistake. Thank you. All right. Well, that makes our analysis even easier. Everything is 0. Right? Ix of 0 minus is 0 amps. Vx of 0 minus is 0 volts. Iy of 0 minus is 0 amps. Vy of 0 minus is 0 volts. Thank you for that catch, because that would have messed things up. All right. At t is equal to 0 plus, we have our 20-volt source, our 4 ohm resistor. Now our switch is closed, so it's connected to the 6 ohm resistor. What do our inductors look like? Open circuits, 0 amp current sources. Absolutely right. So here's Vx of 0 plus. Here's Vy of 0 plus. Ix at 0 plus has to continue being 0 amps because it represents an inductor current. Iy at 0 plus is also 0 amps because it represents an inductor current. We need to figure out what Vx at 0 plus is and Vy at 0 plus. Any thoughts? Right, so both Vx and Vy are 20 volts. Absolutely correct. All right. And now, oh, did you not know about that? And now we can analyze the circuit at t is equal to infinity. So at t is equal to infinity, we have our 4 ohm resistor connected to our 6 ohm resistor like so. And both of our inductors are short circuits. Here is Ix of infinity. Here is Iy of infinity. Here's Vx of infinity. Here's Vy of infinity. So we know by inspection that Vx of infinity has to be 0 volts and Vy of infinity has to be 0 volts as well, because those are voltage drops over short circuits. How do we figure out Ix and Iy? Iy should be 0. I agree. Ohm's law for the other one, right? Okay, so that means 20 over 4 is 5 amps. Okay. So since our ultimate goal was to determine the quantity Iy, we know that I'll do as much here as I can. Iy of x is a1e to the s1t plus a2e to the s2t plus iy at infinity. And therefore iy of 0 is a1 plus a2 plus 0 amps. So our first equation is a1 plus a2 is equal to 0 amps. Are we okay with that? All right, just double checking. So let me go back one smidge here because Taj asked how are Vx and Vy 20 volts at T is equal to 0. So Vx and Vy are 20 volts at T is equal to 0 plus specifically because since there's no current flowing through the 4 ohm resistor and there's no current flowing through the 6 ohm resistor, there cannot be a voltage drop over either of those resistors, right? So if we did Kirchhoff's voltage law with the understanding that there's a 0 volt drop here and a 0 volt drop here, we would have to find that Vx and Vy are both equal to 20 volts. All right, let's go back to our setting up our system of equations. So we know that Vy of T is L2 d Iy by dt, or L2 times S1 A1 e to the S1t plus S2 A2 e to the S2t. So Vy at 0 plus simplifies to L2 times S1 A1 plus S2 A2. So let's substitute in some values here. So Vy at 0 plus was 20 volts. L2 was 2 henries. S1 was -1, so negative A1, and S2 was -6, so -6 A2. This is equation 1. This is equation 2, and we can now solve for the quantities A1 and A2. So my coefficient for A1 in my first equation is 1. My coefficient for A2 in my first equation is 1. My constant term is 0. My coefficient for A1 in my second equation is -1. My coefficient for A2 is -6. And my constant term is 20 over 2, which is 10. Solving, I get 2 amps and the -2 amps. And from this, are we solving for Iy or Vy? I don't remember. Vy. Okay. So I can get the coefficient for my voltage by simply multiplying L2 times S1 times A1. And then my coefficient for the second term of my voltage is just L2 times S2 times A2. So since L is 2, S1 was -1, and A2 was +2, that gives me V, if this will write, -4 e to the minus t. And then I'm going to have 2 times S2 times A2 plus 24e to the minus 6t. And just for the sake of argument, let's simulate our circuit and make sure that we're correct. Keyboard out. Oh, this is going to be annoying. All right, so we have 20-volt source here. 4-ohm resistor, 6-ohm resistor, a couple of 2 Henry inductors. Wire this bad boy up. And I'm going to choose to put my ground on the bottom. .IC I of L1 was 0. .IC I of L2 was also 0. Let's start with 1 second and see what happens. So we want the voltage drop over transistor 2, excuse me, not transistor, inductor 2, which is this guy right here. And we had -4 times EXP of negative time plus 24 times EXP of -6 times time. And it matches exactly. So we must have done everything correct. All right, we've got 25 minutes left of class. What do you guys want to talk about as a very brief review before your exam on Monday?
Would have performing KVL around the outside of this and getting a direct relationship for that source to that current net inductor been any more efficient in the calculations?
Are you talking about at the beginning of our determining alpha and omega naught portion? All right, let's look at that. That's a reasonable question. So the question from the floor is, instead of applying Kirchhoff's voltage law around the right-hand loop, could we have applied it around the perimeter of the circuit? The short answer is yes, we could have done that, but would it have been any more efficient? I don't believe so. Let me explain why. Applying KVL around this loop would have incorporated the current that's flowing through the 4-ohm resistor, right? Because we would have had to have taken into account the voltage drop across the 4-ohm resistor, which is still dependent on that quantity Vx. So it would have added that bit in anyway. So it would have just also happened to have a DC term that we would have had to move around as well. So I think KVL around the right-hand loop is the more efficient choice of a KVL loop to use for this particular problem. But definitely explore those types of things when you're doing your homework and working on the take-home portion of your exam. The two circuits that we have analyzed happen to work well with doing KCL at that top middle node and KVL around the right-hand loop. That's not always the case. So any KVL expression should be valid and can be used. Any KCL expression should be valid and can also be used. Whatever node or loop you choose that helps you separate the variables so that you can get one variable on one side of the equation and the other variable on the other side of the equation is the one that you should do, generally speaking. Any other questions?
The two,
Oh, Ryden's got his hand up in the back. I'll get you to say so. What's up, Ryden?
Just one, scroll back.
Scroll back to the end, sure. Oops, slightly too far.
And the second question is a clarification. So the reason why IY at infinity is 0 is because IX is a short circuit.
Exactly right. So let me scroll up just a smidge here. Okay. So because IX is a short circuit, all of the current here entering this node sees a short circuit path or a 6 ohm resistor path. So all of it will choose the short circuit. You're 100% correct there. Anything else? All right, Skylar, what was up?
so the two general circuits that we've done the past two class periods, are those, like, what difficulty level would you say these have been?
These have been, I would call them easy difficulty. Your homework problems are probably easy to medium difficulty, which your homework has not yet been posted. And then the take-home exam problem is of medium to hard difficulty. So you will, your homework assignment is 2 problems. So you will have a week to take care of 2 medium difficulty problems. And then your take-home exam is 1 problem where you will have a week to knock out that 1 problem. And legitimately, the homework problems probably shouldn't take more than half an hour-ish for you to do of your own volition. Well, I take that back. Because it can take some people longer to do all the manipulation and stuff. But I would say that the homework problems, the homework set, you should be able to get done in 1 session of doing homework for this class. It shouldn't take a wild amount of time. The in-class, excuse me, the take-home exam problem should probably take you about as long as it took you to do those 2 medium difficulty problems. Once you get the differential equation done, it's easy. It's just the differential equation is hard to write. All right, so I think it was Catherine and then Rajan and then Bradley. So Catherine.
Just double checking, the general is not going to be on the in-person.
That is correct. For the in-class portion of your exam, which you will take in here on Monday for the overwhelming majority of you, it is literally 2 questions. Okay. Or let me rephrase that. It's 2 circuits, very similar in layout and structure to your homework problems. Okay. One of the circuits is it has a dependent source in it, but it does not have any independent sources left in at t is equal to infinity. So it's a simple natural response problem where you have to figure out what the equivalent resistance is in order to calculate alpha and omega naught. It is absolutely a series or parallel RLC circuit with a dependent source, no sources left in, or no independent sources left in at infinity. The second question is, so let's say the first one was a series RLC circuit, then the second question is a parallel RLC circuit where there is a source left in at infinity, but there are no tricks Like, there's no dependent sources or anything that you have to worry about. So it is really just effectively two homework problems. One from a series RLC circuit set and one from a parallel RLC circuit set. And you're expected to be able to get both of them done in roughly an hour and a half, which personally does not seem unreasonable, but you guys will tell me otherwise, I'm sure. Was that enough clarification, Catherine? All right, Rajan, what was your question?
So I remember on the previous takeaway that you had us design.
Right, there.
Does that count as designing thing or?
No, I actually need to upload the design. So there is a design project associated with op-amp circuits that I do need to upload for you guys. That's going to be due at the end of the quarter. There's going to be like, I think I give you 5 circuits. I need to get that done today. I actually should have done it like a week ago. There's going to be 5 options. You do 3 of them. So you pick and choose whichever ones you feel the most comfortable with, and I'm happy to answer questions about any of them that you might want to approach. But that's not due until the end of the quarter. There will not be a design problem associated with RLC or second order circuits at all, because there's really not a whole lot of design that you can do.
Which is exam 3?
No, this is the exam that we're about to do.
Okay,
Yeah.
pardon me, thank you.
No, there will be a design problem associated with the exam 3 material, and there will be a design problem associated with the exam 4 material. But this material doesn't really lend itself to a design problem. It just kind of is what it is.
Will those, pardon me,
Go
will
ahead.
those have similar deadlines where we'll?
End of the
assign it
quarter.
And then, okay.
Yep. And I'll try to actually assign it during when we're talking about that material, as opposed to a week and a half later when you've all ostensibly forgotten everything. Anyway, Bradley, what was your question?
So I wanted to ask, whenever we do have like a parallel RLC circuit with a dependent source left in during the transient condition, as well as an independent source, if, to be blunt, like example, or question 5 on homework 8. So we have the dependent source and the independent source on each side of a node. And the current between those nodes is the dependent source of voltage. So
Let me look at homework 8, problem 5, because
Are you gonna ask if we have to do the test source method for that one if I'm already
the answer to that is yes.
question 1. Yeah, what I'm wondering is how we get the dependent source voltage when the dependent source voltage is like incorporating into its own calculation.
All right, so let me see exactly what it is that you're talking about.
To the node that flow through determines what its voltage is. So
So the question is regarding homework 8, problem 5, you said, right?
it's just like the behavior of the dependent source during the transient condition. Connected to the same node as that IA there.
Right. So let me make this larger. Okay. So during the transient condition, the current IA has 2 paths that it can flow. One is up through this path, and the other is up through this path. So it is not simply all of IA flowing into this, so there isn't a circular dependency,
Oh, okay.
right?
Oh, that's good.
So for this particular problem, disconnect, effectively put a terminal. Can I draw on this with this program? I think I can. My expectation of you is to effectively put a terminal here, put a terminal here, and take out the capacitor in series with the inductor to find the equivalent resistance of this dependent source in series with the parallel combination of 1 and 3.
So we need to do step A again for the transient condition. Or, well, the first one is the transient condition.
So step A is determine the equivalent resistance and then use that to calculate alpha and omega naught. You cannot calculate alpha and omega naught without knowing what resistance the 1 ohm resistor in parallel with the 3 ohm resistor and that combination in series with the voltage source represents.
I'm having the issue at part C during the 0 plus.
Okay, so at 0 plus,
VRT would be IA or negative IA times 3 ohms.
no. VR of T, well, no, you are correct. IA times 3 ohms is, or negative IA times 3 ohms is VR. What's the problem with that?
I think the capacitor it was left in as a voltage source at T equals 0 plus.
Okay,
So it was like we had the voltage source connected in series with the dependent voltage source. So I didn't know which to use or if I was supposed to find a difference.
if they're in series, they add together. Voltage sources in series combine.
That is exactly what I was thinking. Okay, thank you.
Yep.
Thank you, sir.
Okay. What's, Rajan?
Yeah, in series, isn't that inductor?
That was
Sure, maybe, I don't know. It depends on what its value is.
So the real thing was, for me, at infinity, there was no, I mean, there was still a dependent source, but there's no other sources.
Right, so
Does that count as a nothing situation?
exactly right, which is why I didn't ask you to solve for it, right? So if there are no independent sources left in at t is equal to infinity, you do not need to analyze the circuit at t is equal to infinity.
So we wind up with nothing if there's no more independent in the situation.
Exactly right, yes. So I'm just looking at this guy right here. So with the switch closed at position A, so our analysis at t is equal to 0 minus. The capacitor looks like an open circuit. The inductor looks like a short circuit. So let's see. The voltage drop over the 3 ohm resistor is going to be 7.5 volts. Or negative 7.5 volts because of this polarity. And the current IA should be 2.5 amps. The voltage VL is obviously 0. The current I is obviously 0. And the voltage VC is going to be 7.5 minus 5. Right, if IA is 2.5, negative 2 times 2.5 is minus 5. So we have minus 5 up here, 7.5 here, 12.5 volts, excuse me. So VC at 0 minus should be positive 12.5 volts. So you have at t is equal to 0 plus, you have a 12.5 volt source here, an open circuit here, so they're not in series because there's an open circuit between them. So what that actually means, there's an open circuit here, and there is an open circuit here, and you have these two resistors in parallel. There's no current flowing in anything.
Oh, okay. So it just all goes 0.
Yeah, so IA has to be 0, right?
Thank you.
Because if you did KVL around this loop, you'd find out that the voltage drop over the 1 ohm resistor plus the voltage drop over the 3 ohm resistor have to add up to be 0, which is only true if no current's flowing. Yeah. So that means IA is 0. And yeah. Okay.
Yes, sir.
Yep. Skylar.
About this same one. Whenever you find I at 0 minus,
Mhm.
can you just, I know the current across the inductor can't change abruptly when you get 0 plus.
Right.
So if 0 minus wasn't
0 amps.
0, could you treat as if I at 0 minus was just like IL of 0 minus?
Yeah,
Does
that's
that make
exactly what it
sense?
is.
Okay,
This I is the inductor.
is the, even though it doesn't have the little L there. you
Right, but
can-
it's still the current flowing through the inductor.
Right, okay,
It's common to the capacitor, the inductor, and the equivalent resistance, which is why I didn't give it a subscript, but it absolutely does represent the inductor current.
okay, so whenever you go to 0+. we're
Because that
replacing
zero
that
acts,
into zero.
yeah.
Okay,
Replace it with an open circuit. Rajan,
So there was a parallel RLC. And that was also dependent, so for solving for REQ, is that also gonna have to be a test source?
anytime there's a dependent source, it's a test source method to solve for the equivalent resistance, yes. And we did that problem in class. I don't know if it was a day that you happened to miss, but I'll get all the videos put up tomorrow morning. But we actually solved, I'd say 80% of the parallel RLC circuit problem with a dependent source in it on, was that Monday maybe?
I think so.
Yeah. So if I have not yet got that video up, I apologize. It will definitely be up tomorrow.
I have another question, sorry.
Yep,
For the design projects and everything, those are by ourselves.
individual, yes,
Individual, don't work with anybody else.
correct.
We can look up stuff on Google.
Absolutely.
Okay,
100%, yeah. And with regards to talking to your peers and stuff like that, that doesn't actually bother me. You just need to come up with your own solution.
right, like if I was.
Yeah, so like for
talking to
the-
Catherine about certain concepts and stuff.
Yeah, I wouldn't have a problem with that.
Hey, did you do this?
The only thing that I actively discourage you guys from talking to each other about is the take-home portion of your exams, because that's cheating. Everything else, while the design projects might be an individual assignment, you can absolutely talk to each other about all that kind of stuff. Because there's 5 different things for you to choose from.
So
and you just-
obviously, if you did the same exact one. then
Right.
that's-
Anything else? All right, I'll see you. Yes.
You know, I mean, when you're generating those general responses to the systems, at least in terms of, well, I guess because it applies to all of it, doesn't matter if it's a certain thing. Okay, so when you're having to solve for the capacitor voltage, for the capacitor current, or that of the inductor, it seems fairly straightforward because those expressions will have direct relationships to the values that you're interested in. So whenever you determine, like, say, coefficients or those constants and stuff, it's kind of natural to just use the values that you get in your analysis that correspond to the capacitor or, say, the inductor. But if you're looking for the resistor,
You need to, so if you're looking for the resistor quantities, so the problem there is that the current voltage relationship for a resistor does not have a derivative-based relationship. So you cannot use them to set up your equations to determine your response. You can only figure out what's going on with the resistor once you know what's going on with the capacitor and or the inductor.
yes. So, okay, so
So
that's.
you cannot directly solve for the resistor quantities,
Okay.
or how the resistor behaves as a function of time, I guess. You
And
have to
you would-
indirectly do it.
And you wouldn't use the values that you derive for the resistor in your analysis at each point to determine those coefficients and constants, right?
Right, because there isn't, when you're
Because
setting
I-
up that
I think
system of
it's-
equation, it involves, you know, a 0th derivative equation and a first derivative equation. Well, there is no derivative equation for the resistors.
Thank you.
Right.
So speaking on top of that, so for example, one of the homework was asking to be off,
Mm-hmm.
and I find odd.
Right.
So my brain is thinking about the simple equation, IR, like R times that time equation. Was that appropriate to do?
So depending on the problem,
So like, yeah.
Oh, really?
but yes, it shouldn't be any harder than that. So let's look at this guy right
I'm
here.
hoping that was right.
Yeah. So let's look at this circuit right here. If I asked you, okay, well, I didn't ask you to find VR in this one, but if I did, if you found I of t, VR is just 5 times I of t, because Ohm's law makes it have to be that. So that's my expectation. If I ask you anything having to do with a resistor, you figure out whichever quantity makes it easiest to solve for, either I of t or the inductor current or the capacitor voltage, and then you use that to solve for the resistor quantity. So let me see what's going on in chat right here. Where would you place the test source here? Let me go back to what I had drawn on. You would place the test source between those two terminals. So you take the capacitor and the inductor out of the circuit entirely, like erase them, delete them, whatever, and you replace at those open circuit terminals is where you place your test source. All right, so, okay, so for this one, it's specifically saying, I ask you to calculate I and VR. Well, I flows into the positive terminal here, so 510 times I is the VR that you're looking for. If I open up homework set number 7, let me find one that I asked for resistor quantity. So this one I'm asking for the current flowing through the resistor, right? Well, that's just this voltage divided by the 2 ohm resistor is the current flowing down to the resistor. It's always going to be related to capacitor voltage or inductor current, because you have to know one of those 2 quantities in order to tell what's going on with the resistor. Yeah, now the simplest one, let me restate that slightly. The simplest way to do it is to take the voltage drop over the capacitor and then divide that voltage by the 2 ohms. And that gets you the current by Ohm's law. An alternative way that absolutely works, but is definitely more tedious, is to apply KCL and say the capacitor current minus the inductor current, apply KCL at this node and then solve for IR directly without using Ohm's law. KCL, KVL, Ohm's law are absolutely always applicable in all of these circuits. So just whatever is the easiest way for you is a perfectly fine way to do it. I try to do the ones that involve the least amount of work because I'm very lazy. Yes.
So you're saying on this one, we could have done the VC over the 2 ohms and that would have given us the current going through the resistor. That would have been just fine.
Yep, absolutely.
So that only
That's
works.
kind of the reason why I asked you to solve for VFC.
So that only works because
The
they're
capacitor
all
and the
in-
resistor and the inductor are all in parallel.
But
Yes.
for like other situations and stuff, it would usually just be like B of R over 2 solving for it. Like you have
Right.
to keep with the same.
Yeah, so in the series RLC circuits, it was always I times R because I was
So
common
I-
to all of the elements. And these parallel RLC circuits is always going to be V over R because V is common to all of the elements. If I ask you for a resistor quantity in one of the general RLC circuits or the general second order circuits, then you'll have to do something else. So like, let's look at the problem that we worked on Wednesday briefly. Okay. So if I wanted this quantity, wait, sorry, that's not, that was when I was going over general RLC circuits, so that's not remotely helpful, or excuse me, parallel RLC circuits. Here's this guy. So if I wanted the voltage drop over resistor R2, well, it's the same thing as VC.
Right.
If I want the current flowing through resistor R2, it's just VC over R2. If I wanted the current flowing through resistor R3, it's just IL. If I wanted the voltage drop over resistor R3, it's just IL times R3. And if I want the current flowing through this guy, let's say the switch was closing at A or something like that. There would be a contribution from the current source as well as a contribution from the capacitor current and the inductor current. Kirchhoff's current law has to be satisfied.
Right.
So it's always going to be falling back on those simple relationships, KCL, KVL, Ohm's law, in order to get the resistor quantities. Always, always, always.